So I'm going to talk about this is some work I did with Andrew Rosen. I guess I will add him in here. On adding in some dependency plugins into Parsl. The background for this is, if you think about the language side of Parsl, so not the task execution side, what we did was, Yadi did this when I wasn't around. We try to use Python syntax, but sort of add in Parsl semantics on top of Python syntax. And Parsl semantics kind of means how you would expect Python to work as much as possible, but then with cool workflow stuff like concurrency added in there. So the comparison to that is Swift, which was the thing before Parsl. We had a completely new, unfamiliar to users language, and we could do anything we wanted in there, but it was unfamiliar to users. So that's sort of what the Python syntax but Parsl semantics motivation is. And so what I've been fiddling with here is how dependencies work. So we're trying to do Python syntax, and so you might have an expression invoke A, and the parameters are invoke B and invoke C. And in just in normal Python, that executes as we're going to run B and get an intermediate value, then we're going to run C and get an intermediate value, and then when we've got those two values, we can invoke A with the two intermediate values. And in Parsl, sort of the Parsl special magic is that we can see that there's some potential concurrency here. We can run B and we can run C at the same time, and then when they're both done, we can run A. Excuse me. So that's the sort of concurrency, magic concurrency unlocking that Parsl gives you on the language side, on top of Python. And the way that works is it's all mediated by these future objects, which come from the concurrent.futures package. So to execute this little tiny workflow in the middle, we basically have defined these A, B, and C as Python apps, and we're just going to run all of them at once. And that's going to happen really fast. And now we're going to have three Parsl task definitions and three futures that represent the completion of that. And then there's the data flow kernel bit of Parsl that says, all right, I can figure out from how those futures are tied together what the execution order is, and that I can run two tasks at once. And then I have to substitute in their results into the third task. And that all comes via future objects. So users have imaginations. And when we're giving this idea that it's Python syntax, but some kind of magic Parsl semantics, users who have imaginations start imagining things, and they start imagining things that seem obvious that might work, and turns out they don't always work. So what this talk and this pull request 311 and this feature is some imaginations that various users have had over time, repeatedly, and discovered it hasn't worked, and I eventually got around to implementing it. Another example of this sort of users imagining things and it getting implemented is the overloaded operators work we did in 2904, PR 2904. So here's this specific imagination. What if instead of having an expression like this, ABC, and having Parsl extracts and parallelism here, what if I want to pass in a more complex structure? So I'm calling A, but what I'm passing in is a dictionary. And inside the dictionary, I'm sticking in two little task invocations. So this is a bit contrived, but where Andrew wants to use it is he wants to be returning more complex structures as he makes higher level components for his users to build their workflows out of higher level components. And some of those components should return dictionaries with various futures inside them instead of just being a single future. And hopefully we'll get him to talk about that in another talk. But from the technical side of things, it looks like this. So this doesn't work. Okay. This app A is being invoked. It's not being invoked with a future. It's being invoked with just a normal object, which is a dictionary. It happens to have these futures inside, but whatever. As far as the DFK is concerned, this is just a dictionary. So there's nothing to wait for. We can run A straight away and pass in that dictionary. And that doesn't work. It explodes because you've written your code assuming that this task has run and had its results substituted in, just as would happen here. And so everything basically explodes. But it's a pretty, like, hopefully you can see that you would hope that this would work, right? That it would run and these would run first and then their values would get put into the structure. So it's a bit of historical context. In Swift, which was Parsl version -1, this worked just fine, because there wasn't any distinction between values that live in futures and normal values. We sort of figured out that that's how it's got to work in Swift, and then part of the move back to Python meant that this distinction got added back in, and now that's more trouble for users. And that's one of the trade-offs of moving away from Swift and moving to being embedded inside Python. And then certainly as far back as 2020, users have been trying to do stuff with this. Someone made a PR in 2020 that did some iteration like this, but why only lists, why only tuples? It was only one level deep. At the time, I was unhappy with how that was going to work. But 4 years later, we're in a position to maybe do something a bit better. So I spent a few hours hacking on this idea 3 months ago. Andrew's played with it since then. We've done some iteration, not a huge amount of development since then, and it's finally got merged in the last week or so. So this sort of change is quite conceptually big. It's not a lot of lines of code. It's expensive in the sense that performance could change quite a lot, and the semantics could change quite a lot. Like, we want to change the semantics to satisfy that imagination. And there's lots of opportunity for bugs. Even just making this presentation, I think I fixed 3 bugs in the new implementation that I put in. So that sort of thing drives me in the way I think of Parsl stuff now, as putting in a plugin interface. So that by default it behaves the same, but you can plug in different stuff here. And so what PR 3.1.1 merges is a plugin interface, a plugin that's the old behavior unchanged, or hopefully unchanged, and a plugin with this new behavior that understands how to resolve these deep structures and complex structures with futures embedded inside them. Okay, so I'll explain the plugin interface. We've got the data flow kernel. It looks at futures that you pass in, and it uses them in 2 places. One is to delay task execution. So if I've said run application A with these 2 futures as parameters, the data flow kernel will delay trying to run task A until both of these futures are marked as done. Okay. And then the other thing it uses futures for is when you invoke A of future 1 and future 2, what it actually invokes when it's time to run things is A, but with the values contained in these futures substituted in. So they're 2 very similar uses. They kind of, it's rare to, when you talk about things publicly, to distinguish those uses. You just say, oh, it's a dependency and this is how it works. But they are different steps, and they don't have to be the same futures even. So what do we want when I run some code like this? A with a dictionary with 2 futures inside it. Well, we want to wait for these 2 futures to be done. And then when they are done, we want to invoke A, but with some kind of reconstructed dictionary. So I want to make a dictionary that kind of looks like this dictionary that we started with, but deep inside it, possibly to arbitrary depth, I want to substitute in the results. So you could imagine there's A, then some kind of substitution function going on. Okay, so there's a plugin class, basically two different sets of if statements in the DFK turn into calls into this new plugin class, which is has two methods. One called traverse to gather, which says if I give you a parameter, tell me all the futures I need to wait for that parameter. And then and so that's how the DFK can iterate through all of the parameters of an invocation and say, how do we know what to wait for? Well, this dependency resolver plugin for every parameter will give you a list of all the futures you need to wait for. So this will get called once per parameter. And then when all of those futures are done, we're going to traverse the parameters again to unwrap them and go from this sort of dependency form into the value that we can actually invoke the app with. And so we go over it again with traverse to unwrap, and that says, I'm going to give you an object and you're going to unwrap it and give me the resolved form. Okay, so let's go back here. This is the resolved form. This is what I mean by being unwrapped. Okay, it kind of looks like this, but it isn't a completely trivial mapping from this to this. So what does the old behavior look like? The old behavior in the old implementation had a lot of if statements that basically say, is this parameter a future? If so, we're going to do dependency behavior on it. If it isn't a future, then it's just a normal object and we don't have to do anything. And that becomes this default behavior, default dependency resolver called the shallow dependency resolver. And so here's basically the whole source code for that. The default behavior, if we give you an object, is, well, we don't need to wait for any futures at all. If I've just given you an arbitrary object, we can assume that object is ready to use. And when I want to unwrap it, if it's an arbitrary object, we can assume we don't need to do anything. If I give you the number 7, it's ready to use immediately. Okay, we don't need to wait for anything. And if I want you to prepare the number 7 to be passed as a parameter, it's already there. It's ready, right? Just return that number 7. So that's the else statement. That's the else clause of all of these if statements turns into this. And then the only special behavior we have is if someone uses a future as a parameter, we need to wait for that future and to prepare it for use by the app, we extract its result. Okay, so this is all the cases where this is instance if statement fires in the old code. It's these two bottom cases. Okay. Okay, so that's the default behavior. It just looks like code rearrangement. The new behavior is if you want to pass in a list of futures or a list of a set of dictionaries that contain futures, whatever, to arbitrary depth, there's a thing called the deep dependency resolver, and that has a lot of type-specific implementations in it like this. So for tuples, lists, and sets, what we say is we're going to go over every element in that sequence. We're just going to iterate over it. We can iterate over all three of these the same. And we're going to say extract all of the futures that we would need from every element of that. So it's a recursive call, a recursive traversal through that structure. And we extract all the futures. This really should be a future, call it F. And we extract all the futures from all of the sub-elements and combine them together into a big list. Okay. So basically, we'll walk the entire object tree looking for futures. And so an app won't run until all the futures, however deep in a structure, have completed. And then to unwrap them, this is code is a little bit weird looking, but what we do is we iterate over all the elements of that tuple or that list or that set. we recursively unwrap that element, and then this gives us a sequence, and we turn that sequence back into whatever it started as. So if we're traversing a list, we iterate over, we turn it back into a list. And then the other behavior is the same as on the previous slide. So eventually this will discover some futures and it will unwrap them using .result, or it will discover some things like the number 7. And we have the same default behavior as on the previous slide. Cool. So there's sort of, this implementation really gets away from having any if statements about types. Okay. We used to have, or the code used to have if statements. And now instead of any if statements that know about all the types, you have these registrations of here's how you plug in a new type that we know how, that someone knows how to walk over and pull out futures and rewrite. Dict is the other thing. So the two sets of things that are implemented are list tuples and sets that behave one way, and then dict. The dict isn't a sequence, it doesn't behave quite the same. What we have to do is recursively traverse over all the keys and all the values, because a key might be a future as well. And then to unwrap it, we traverse over every element and pull out the key and the value and reconstruct the dictionary that way. So that dict I was using earlier on gets reconstructed here, and this is the code that reconstructs it by making a new dictionary that consists of what happens when you unwrap all the keys and values recursively. So that's how it works. It's opt-in behavior. The big reason the two reasons I made it opt-in are that I'm unsure about how buggy it will be, and I'm very unclear about performance. So if you look at things like this, it's reconstructing all of the objects that it unwraps. And I don't quite have a feel for what that performance would be like. But because it's opt-in, I don't mind that much. Like it gives us a way to start experimenting with this and using it as a language feature. So I would hope that the performance for the default case, the shallow case, hasn't really changed, I hope. But for deep stuff, maybe it's going to behave similarly to how serialization and deserialization works when you're using an HTEX, because that does the similar kind of recreating an object on every invocation. So maybe it's going to behave like that. I don't know. It would be interesting. I might get around to doing some performance work eventually. And then that API unlocks a few things that might be interesting to experiment with. So the DFK doesn't care what a future looks like anymore. Okay, so you might have things like other things you might want to use it as a dependency. So maybe you're doing some stuff in async.io, and async.io has its own future class. Well, maybe you want to be able to use those as Parsl dependencies. This is a plugin API that would let you put that code in without having to change the core of Parsl, for example. Or maybe there's other stuff that kind of looks like a task that completes and has a value. This API is how you could wire in that dependency as well. One thing I realized is that file staging, which I talked about last time, I think, starts looking very similar to this pluggable dependency code. You have a special object type, a file, and at launch time, you go through, you find all the files, and then you turn it into a special future that will complete. And then when it completes, you substitute that's a new file object back into the app. The big difference here is this code launches potentially heavy staging work rather than just pulling out existing fields, but the API doesn't prohibit that happening at all. And fast staging, I've come to realize, is not as fundamental to Parsl as it was in earlier versions of this work. So maybe this is an interesting way to pull some of the file staging code out of the core of the Dataflow kernel and make it its own slightly more pluggable modular thing that we can ignore a little bit more. And we just sort of have this notion now that there's a pluggable dependency. You've got some kind of interesting object. We understand, or a plugin needs to understand how to make the dependency resolution happen. What does it mean to wait for that dependency? What does it mean to substitute its real value? It's a plugin point that gives you this opportunity to mess with parameters in interesting ways. But what interesting means here isn't defined by Parsl core anymore. That's what the plugin facilitates. So one, for example, thing I made up is if you're doing proxy store, this would be a place to say, oh, look, here's a large parameter we're going to push to proxy store right now, rather than later on at serialization time, maybe. Okay, so the conclusion of that is, I think for a lot of users, it feels natural to nest futures inside complex structures. I don't think at that level it's particularly weird. It is quite complex to implement, though. There's a plugin API to experiment with this complexity. It does list tuple sets and dicts at the moment. It's extensible. Maybe we'll discover more types that we want to have implemented in the core code. Users can plug their own stuff into that pretty easily as well. The performance is unknown. I think there's maybe interesting things to discover about other kinds of dependency objects more generally, and sub workflows that are launched that way. And I'd like to big thanks to Andrew, who's been the user driving this, who's really worked a lot with me to understand how things should work.